Good afternoon, everyone. So let's begin with today's Jugalbandi, several complex variable versus single complex variable. Before starting the presentation, let's go into some historical development of these two topics. So single complex variable is a classical topic which started to shape in 18th century. It is greatly owed to the discoveries made by mathematicians like Cauchy, Riemann, Euler, Weierstrass. In single complex variable, we study function on a complex plane, their properties and their results. Whereas several complex variable is a very recent topic, very recent in the sense it just started a century ago. So several complex variable, or as we also known as multivariable complex analysis, started to recognize as an independent topic of interest from the beginning of the last century. It is greatly due to is mainly due to the Hartog, who made a discovery, which we'll see in our presentation today. Before getting into further details, let me briefly tell you what we are going to discuss in today's presentation. So first we'll set up the stage to state both the stage for stating the result for both the topics, and then we'll move on to holomorphic functions. We'll define holomorphic function in a complex plane. Also, what do you mean by holomorphic function in several complex variable? Then we'll move on to the results which will hold true for both several and single complex variable. And at the end, we'll see the results which are only valid in several complex variable. That is, results where several complex variable stands alone. So a complex plane is a set of points which is defined as z equal to x plus iy, where x comma y are belongs to R2, where x and y are called real and imaginary part of complex number z respectively. So, and n-dimensional complex plane, which is n-dimensional complex coordinate space, is the copy of n complex planes, complex space. So typically a point in a complex n-dimensional complex space is written as z equal to z1, z2 up to zn, where each of these variable comes from the complex plane. Now, moving on, let's define what do you mean by a ball in the complex plane. So the first open set we study everywhere in analysis or in topology is a ball. So open ball in complex plane C. So let's define a ball B is centered at origin and has a radius r, which is contained in complex plane C. So the definition of the ball is set of all points z in complex plane C such that z minus 0 is less than r. Okay. We can also define this is the mode, and we can also define using Euclidean metric, which is actually same in single variable. This is an Euclidean metric. But if we increase the one dimension more in complex space, so consider C2, the norm in C2, the two sets ball 0 comma r, which is defined as set of all z, say z1 comma z2 in C2. So in C2, such that z1 zi is less than r, or I equal to 1 and 2, and which is not equal to z1 comma z2 in C2 says that the Euclidean norm is less than R. These two are not equal in the sense they doesn't represent the same set. So we call this set the first set. Sorry, that was a mistake here. This set here, we call this as a polydisk. So this P2 in P2. And this we call as a normal Euclidean ball. These two are two different sets, but they are topologically homeomorphic. So we can find a map such that the map is continuous 1 1 on 2 and its inverse is also continuous. So let's define it once more. So let a point in Cn and R be a radius. Then Bn a comma R is defined as set of all points in complex plane such that the Euclidean norm of z minus a is less than R. Whereas polydisk around a point A with the radius R in R plus Rn, then the polydisk around of polyradius R, the radius R can take different values. So R is a vector actually. Before the R was a scalar. Here it was a scalar. But we can define R as a vector as well. So how will you define a polydisk of radius R around a point A is equal to the set of all points in complex plane such that the norm of Zi minus Ai is less than R. So on each coordinate, it looks like a disk. So it's a product of basically polydisk is a Cartesian product of disk. Now let gamma be equal to these delta 1 are disk in complex plane. So we are taking the Cartesian product of n polydisk. Delta 1 it means that it's a boundary of the disk. So we are taking the Cartesian product of boundaries of n disk. Let us call this as a distinguished boundary of a polydisk Pn, which I mind you is different from this topological boundary. So topological boundary in the sense like delta, let's say Pn, delta Pn be the boundary of polydisk, which is not equal to this distinguished boundary. As I stated before, polydisk and ball are homeomorphic. So this actually has an interesting consequences. We'll see it further at the end that polydisk and ball are very special. Now let me just note out some preliminaries. So let me introduce a multi-index notation. So nu belongs to n naught n, which is a vector, and this vector each value is a natural number including 0. Mod of nu is the sum of all these coordinates. Z nu with z belongs to Cn is equal to the product of z1 raised to nu1, z2 raised to nu2 up till zn raised to nu n. Whereas nu factorial is defined as nu1 factorial into nu2 factorial up to nu n. As we have seen a polynomial in complex plane. So polynomial in complex plane is which in simpler notation we can write as f of z equal to a naught plus a1z plus till an z raised to n, which is a polynomial in complex variable of degree n. Similarly, we can define a polynomial in Cn, which is p of z is equal to summation mod of nu is less than d, a nu, z nu. Let me just elaborate with an example. What do you mean? We'll just take a case. Let's say d equal to 2. Say n is equal to 2, then p of z, typically p of z will be summation nu less than or equal to 2 a nu z nu. So nu is a vector actually. So what all possible values it can take are there are two natural numbers which we can put the values inside this. Let's say A12 is Z11, Z22 plus A21 is Z12, Z21. So this is typically a polynomial in CN. Okay. Moving on, let's just see an example of what a function from Cn to C looks like. So let's consider f of z1 comma z2 till zn, function of these n z variables, which I'm just writing as z1 plus z2 plus z3 plus till zn. So this is a function from Cn. It takes value from Cn and spits out values in complex plane C. Now let's have an example from of a function from Cn to Cm. So it'll take values from Cn and split out values in Cm. So let me define g of z1 comma z2 comma till zn, which is a vector valued function. Each of these function g1, g2 till gn are functions from Cn to C. So you are just putting g1, g2, gn as a function from Cn to C. In each coordinate, it's a function from Cn to C, and in overall, it is a function from Cn to Cn. Now let's see holomorphic function. So in complex planes stand out different. So complex analysis stand out different from real analysis due to the special kind of function. The functions are called holomorphic function. These are the functions why we need to study complex analysis as a separate subject apart from real analysis. Holomorphic function are very special in the sense, like if we have a function, so a holomorphic function has this property. So if I have an holomorphic function, and if it is differentiable once, or in fact, let's consider just a function of Cn, function from C to C, and say that function is complex differentiable. If the function is complex differentiable, then I can guarantee you that if it is once differentiable, then it is infinitely differentiable. This is one property. Second property is if the function is complex differentiable, it's like once differentiable, then on a domain which is different, on a domain where the function is differentiable, the function can be locally represented as a power series expansion, which I'll explain you in the next slide. So complex differentiable, holomorphic function are one and the same. So we just use two different names for complex differential function to say the similarity between the real differentiable function, but the holomorphic function and complex differential function are one and the same. So let me define formally what do you mean by a holomorphic function. A complex valued function f defined on an open subset G of C is called holomorphic in G if at each point W has an open neighborhood U of W such that the function has a power series expansion f of z equal to summation n equal to 0 to n an z minus w whole raised to n, which converges for all z in U. What do you mean by this is, if my function is holomorphic, then I can locally represent my function as a power series expansion, which means that suppose I have a function g, which is from C to C, say this is a complex plane. Sorry, and this is the complex plane. So what I'm saying is, my function is holomorphic, which means that at each point W in the complex plane, in the set G, I can find a neighborhood, say U, say UW. On that neighborhood, f of z can be written as a power series expansion as mentioned before. So so locally it can be represented as a power series expansion. Now if I can write a function in the power series expansion, then this is just a polynomial with a degree is unbounded, right? So polynomials are easy to differentiate. So a polynomial of degree d can be differentiated d plus n times. So of degree d can be differentiated d plus n times until it gets to 0. Similarly, this function is written as a polynomial expression of infinite degree. So I can differentiate this function infinitely many times. So as I stated before, holomorphic function complex differentiable function are one and the same. And this is the remarkable property of an holomorphic function. Now, the question is, can we extend this property in higher complex plane, say in C2 or Cn? The answer is yes. So let's define the holomorphic function in Cn. But before that, let's see some examples of how a function, see some example of holomorphic function in complex plane. So the first function, f of z equal to z. Now, for function to be holomorphic, I need to write this function in a power series representation. This function is already written in power series expansion. To see this, ai z raised to I equal to 0 to n. So ai is 0 for I equal to 0 and for I greater than 1. So ai is equal to 0 for I equal to 0 and I greater than 1. And a1 is equal to 1. So it's already written in power series expansion. So this function is a holomorphic function. Now consider sin z. As you have seen in real variable analysis, sin z has a series expansion. Just replacing x with a complex variable, this will do our job. So sin z has power series expansion, and hence it's a holomorphic. Again, e of z has again a power series expansion. Similarly, but now consider the fourth example. Summation n equal to 0 to infinity zn. Now this is a power series expansion, but this function is holomorphic only on mod z less than 1. So it's holomorphic only on the unit disk, inside the unit disk, not on the unit disk, not outside the unit disk, but inside the unit disk. Because if you see, if you consider the point on the unit disk, the summation will be, if you sum that value, it will be unbounded. So for a holomorphic function, the series should be convergent on the set we are defining. Now, let's see a non-example of holomorphic function. Let's consider the same function, f of z equal to summation n equal to 0 to infinity zn. For now, the domain is outside the unit disk. So we are considering all the points outside the unit disk. On this point, the series is divergent. In the sense, it will not converge. And second example is f of z equal to z bar. Now, we can't write this function in terms of z. The best way, the best possible thing it can have is, we have the property that z bar into z is mod of z square. So if you want to write z bar in terms of z, the best thing we can do is z bar equal to mod z square upon z. But we want a polynomial, so the polynomial should, the z term should have a positive degree, but here it's a negative degree. So the best we can do is we can write z bar in this term. So this is not an holomorphic function. Now let's see the definition. What do you mean by holomorphic function in Cn? It's the same definition, but just we are including we are including more variables. So complex variable function f defined on an open subset G of Cn is called holomorphic in G if each point W in G has an open neighborhood U such that the function f has a power series expansion f of z equal to a nu z minus w whole raised to nu, where mu is less than infinity, which converges for all z in U. So the set of all function holomorphic in G will be denoted by O script OG. So it's the same definition as seen in the single variable case, but we are including more variables here. Now let's consider some examples. How what a holomorphic function in Cn. First example, f of z1 comma z2 comma z3 is equal to sin z1 plus sin z2 plus sin z3 on C3. Now locally you can write sin z1, sin z2, sin z3 separately in their own power series. So in all we are so you can combine all these power series in one power series, and hence the function is holomorphic, as we can write the function this function as a sum of power series expansion. Similarly, in each term, E of Z1 can be written as a power series expansion. E of Z2 has a separate power series expansion. If you multiply them, we get again a power series expansion, and hence it is holomorphic. Another example, so the third example is separately summing Z1 raised to n, Z2 raised to n. So these are exactly our fourth example in the single variable case. And now see on the set which is defined as D cross D. On unit disk, the function is holomorphic. But if you take point apart from the unit disk, outside of the unit disk, the function doesn't become holomorphic. Now, if you have observed that if in each separate variable, if the function is holomorphic, then the function is holomorphic overall, right? So this is our observation, but Osgood proved that. So if we have a complex value function f is continuous in open set G and is holomorphic in each variable separately, then it is holomorphic in G, which means that if suppose I have a function, say G of Z1, Z2 to we have a function like this. Now, if I want to, this is the function from C2 to C. Now, if I fix Z1 equal to some constant K and consider function, say Z2, G of K, Z2. Now, this function is from C to C. Let's call this function C. So now this function, what Osgood lemma says that if this phi function is holomorphic for Z2, similarly, if we can define it for Z1 as well, phi1 dash, and considering the other variable constant, say Z1 comma K tilde, if phi and phi dash separately are holomorphic, then my whole function, so G of Z1 comma Z2 is holomorphic. So if you want to create examples of holomorphic functions from Cn to C, you just need to check if the function are holomorphic in each variable separately. So let's see some of the results from complex variable, single complex variable. The first result is Cauchy's integral formula, which is very famous actually. This is the important theorem which will help to lay out every other result in complex single complex analysis. So it says that let f be a holomorphic function on a set G contained in set C that contains a closure of a disk D if C is the boundary of the disk, which means the circle, with positive orientation. Then f of z can be written as 1 over 2 pi I integral over the circle f of s minus z into ds. Now, what does it mean that suppose I have a domain G and I have an open unit disk inside this. Let me draw it here. Now it says that if I know the value of function on this boundary C, then I can know the value of the function at each point inside this disk. See, so for any point inside the disk D, f of z, I have to just integrate this along this curve C, f of 2 pi I, C, f of s minus z ds. The only thing I need to know the value inside the set in a disk D is just I need to find out what are the values on the circumference of the disk, which is the circle. So on the boundary of the disk, which is the circle. Can we have such kind of formula in higher complex plane, say, or not? So the answer is yes. We have such a formula. So to state that formally, let f be a holomorphic function on G that contains a closure of a polydisk. Now here, instead of a disk, we are considering polydisk. Let gamma be the Cartesian product of n boundaries of a polydisk, which are basically circles, Cartesian of a circle, base distinguished boundary as we have defined earlier. Then f of z is defined to be 1 over 2 pi I whole raised to n. Here n is there. Previously there was no n, and we are integrating separately on each of this boundary of the disk. So this is for multivariable case, which looks similar, just an extension of single variable. Now let's see. Results which hold only true, which holds true for both several and single complex variable. Now the thing is, Osgood's lemma. Due to Osgood's lemma, we can prove similar results which are there in single complex variable to a higher complex variable. So Osgood's lemma was an important step to prove similar results in both several complex variable. Now, one of the famous result in a single complex variable is, say you have two holomorphic function in a connected open set G. Now these results are true for both, so I am just mentioning the single case in a bracket and multivariable case as it is. So let me formally state what identity theorem is. If f and g are holomorphic function in an open connected set G, and f and g are f equal to g for all points z in a non-empty open set subset U of G, then f and g will be equal at all points in G. Let me tell you what it means. Suppose I have a set G, and I have a subset of this set, say U, and I have defined two functions, f and g on G, and use the set where on U f is equal to G. Then the theorem said that if this happens, if I find a set on which f and g are equal, then I can say that the both functions are equal on the biggest set. This implies f will be equal to g on the whole set. So we just need to find a small set on which the two functions agree. Then I can make this function equal on the whole set G. Now, do we have such kind of analog in higher complex plane? Let's see. Sorry, it's already is there. So we are setting the result. Sorry for that. Results are already there. Now let's see the second result, maximum modulus principle. Now, what do you mean by maximum modulus principle? Theorem. Sometimes it's called principle as well as theorem. So if f of z is a holomorphic in connected open set G, and if there is a point W in G such that f of z, mod of value of f of z, is less than or equal to f of W for all points z in some open neighborhood of W, then f of z equal to f of W for all points in Z. So which means that if I have a set G, and if I have a point W, and suppose I have a neighborhood, say U, say neighborhood of W, say U of W, on U of W, if f of z is less than or equal to f of W, then it says that the function is basically constant. Which means that, in other words, they state that the maxima of the function will never lie inside the set. If it lies inside the set, which means that it's basically a constant function, it will never lie inside the set. So that's the maximum modulus principle, or the theorem sometimes it's called. Similarly, there's one more result, Lively's theorem, which says that if f of z is holomorphic and bounded on C, so on complex plane, say let's consider the complex C1 case. I have a complex plane, and if my function is holomorphic on all of the complex plane, and the function plus the function f of z is bounded on the complex plane, then it's basically my function is a constant function. If these two properties satisfy, which is holomorphic on the entire plane and bounded on the entire plane, then my function is constant. This theorem is true for both Cn as well as C. Now, let's see where the several complex variable stands alone. I mean, there are only results where which are true in several complex variable. Before that, let me introduce some definition called domain of holomorphy. Now, let me state it formally. Let U be a domain. The set U is a domain of holomorphy if do not exist a non-empty open sets V and W, with V is contained in U intersection W. W does not wholly contain U, and W is connected, such that for every holomorphic function which is defined on the U, there exists a holomorphic function capital F on W, such that F and capital F and small f agrees on the set V. So let me just clarify. Let me explain what does it is. So domain of holomorphy is basically if I have a holomorphic function f on a set G, and I want to extend this holomorphy on a bigger set. Can I do that? Basically, this is the question. If I can do that, if I can't do that on a set G, then my set G is called domain of holomorphy. I further can't extend that set. But if I can do, then I have to take the maximal set on which the function f is holomorphic, and it can't be further extended to any bigger set, so that the holomorphicity still remains. So domain of holomorphy is the maximal set on which the function agrees to be holomorphic. Now, why don't we in complex analysis, if you have studied, we never talk about such things. So domain of holomorphy, we always consider the domain as a domain itself, but we don't mention it as a domain of holomorphy. Why is it so? Because every set in a complex plane is domain of holomorphy, whereas in several complex variable there are some sets which are not domain of holomorphy. Let me tell you what does it mean. So consider a disk. I'll define a point. I'll define a function f from a disk to a complex plane. Let me define f of z equal to 1 over z. Now observe that at point z equal to 0, the function is not holomorphic. It's unbounded, right? So I'll take a domain. I'll take my new set G. Let me define a new set G, and I'll remove D. I'll remove the bad point 0. Now on this set G, the function is holomorphic, right? I can the function behaves nicely as if I remove the point 0, the function doesn't blow up. So G is what? So on G, the function is holomorphic. Now my question is, can I make some arrangement such that my G will include the point 0, 0, and the function still becomes holomorphic? The answer is no. So this G is domain of holomorphy of this function. So take any set on a complex plane, say this set, and I'll consider just one point on the boundary, say point P, which belongs to the boundary of, let's say this is G, this boundary of G, and I will define a function f such that f is equal to 1 over z minus P. Now, if I want to extend this function to a bigger domain than G, I'll fail at the boundary. I have to surpass the boundary. So now every set in the complex plane is domain of holomorphy. Okay. Now this doesn't happen in complex plane. In a higher variable. Now let's see an example of domain of holomorphy in Cn. So I want to produce an example of domain of holomorphy in Cn. So what I will do is I'll take a set of a complex plane C, say take set G of complex plane C, What I'll do, I'll just take its Cartesian product n times. And I'll call this set as G hat. And G hat is in Cn. And now this set is domain of holomorphy. See, we have created an example of a domain of holomorphy in Cn. Now, let's see, is there a set where the set is not domain of holomorphy? This is the startling discovery made by Hartog, and due to this discovery, people were looking at several complex variables in different way. As we have seen previously, we were just merely increasing one variable and extending the definitions or results in a linear fashion, just to in linear fashion from single variable to the higher complex variable, right? But this discovery made by Hartog changed the perspective of looking at several complex variable to as an independent study, to look as an independent topic of interest. So let me state formally what Hartog's theorem was. So if I have a disk, polydisk, and I remove some portion of the disk, so basically a concentric disk, and if I define a holomorphic function on that disk, then there is a holomorphic function f on the domain such that f restricted to this domain, will be equal to f. So what it means that, mind you can't draw a domain so set in C of C2 or Cn, because if you want to draw, then you have to project it to Euclidean plane, and say if you want to draw a domain in C4, you need to have 8 dimensions to plot it. So Cn is basically R2n, right? So you can't plot it. So what I will do is I will mod out Z. So what I mean by this, let's say is Z1. Let's say a function this set is in C2. Z1 comma Z2 is in C2. What I'll do, I'll just take mod out the values. What does it mean? That in a C2 plane, I'm just measuring the distance of the Z1 coordinate from the origin, whereas Z2, plotting Z2 as I'm measuring the distance of second coordinate from the origin. So I'm just taking the mod values. Now I can plot this plane is called absolute plane. In absolute plane, I can draw polydisk. Polydisk means D2. So polydisk of radius r, center at 0, can be drawn like this. With each of them, each of these length of this axis and this axis is r. Now let me draw omega here. So omega is d2 0 comma r minus the set d2 0 comma r by 2. So I'll just measure r by 2 here, r by 2 here, and this. So let's see again what Hartog's theorem says, that if I have an holomorphic function inside this domain, then I can extend this holomorphic function to the whole domain. Whereas we have seen in a single variable case, as a disk example, I have a holomorphic function f of z equal to 1 over z. This function is not holomorphic at point 0, and you can further extend this domain to the whole disk, but here we can. So here's the point, here's the difference between two cases in things happen in complex plane and higher complex dimensions. So for the proof, it will require some knowledge of single complex analysis. So pardon me, because as I mentioned in the prerequisite, I said it's not necessary, but for this proof it is necessary. So let me check the time. I don't think so I can do that. So what I'll do is I'll skip the proof. At the end, if time permits, we'll look at the proof. Let's see the next result, where several complex variable stands alone. In single complex analysis, in single complex variable, we have a theorem that if I have a zero of a of holomorphic function, the zero of holomorphic function is always isolated. What do you mean by that? Let's say let f from G to C be a holomorphic function, and let z naught belongs to G be its 0, which means that f of z naught is 0. Now what it states that z naught is isolated, which means that if I take a point z naught in this complex plane, then I can draw a neighborhood sufficient sufficient ball of sufficient radius such that no other zero lies inside this set of no other zero of the function f lies inside this set, which means that if I have z1 and z2 two zeros, then I can always separate those zeros. They are not basically they are not limit point, so we can always find a sufficient ball of sufficient radius so that we can separate these two zeros. So this happens only in single complex variable. Now coming back to the theorem, non-isolated zeros. So the proof of this is very simple, and we can use the previous Hartog's theorem to state this proof. Now suppose we'll prove this using contradiction. Now suppose now my p, the 0, is isolated. If it is isolated 0, then I can find a sufficient a disk, a polydisk of sufficient radius such that the 0 is isolated. So no any other 0 is included in that set, which is polydisk such that set of all points in Cn such that f of z equal to 0, intersection d and p comma r is only the point p. Then let's define a function g of z which is equal to 1 over f of z. Now observe that f of g of z is holomorphic on dn p comma r minus p r by 2. So let me draw it here. So this is of radius r, this r by 2. Now it says that so the point p is here. Now it says that you can see that the function g, which is 1 over f of z, is holomorphic in this, and this disk d has no any other 0 apart from point p, and I have removed that 0. So what I have right now is this function g of z, which is 1 over f of z, is holomorphic. So if suppose there was a 0, then 1 over f of that 0 will be 0, and this g of z will be unbounded. So p will be a bad point. So which is holomorphic on this shaded area. Now the Hartog's theorem says that now this G can be extended to the whole polydisk, which means that by Hartog's theorem G continues analytically to this whole set Dn. In particular, G is well defined at P, right? G will be well defined at P. So F cannot vanish at P. So F cannot vanish at P, which implies that if P is not a 0, but which is a contradiction because we have started with P being an isolated 0. So this is a short proof of saying that holomorphic functions has a holomorphic function in Cn n greater than equal to 2 has no isolated zeros. Similarly, we have no isolated singularities as well. Moving on. Now the question arises, what now I have given a definition, I have given an example where the domain which I have defined is not a domain of holomorphic. Now how can you say given a domain is holomorphic or not, and is there a way to find out the given domain is holomorphic or not? So the answer to this problem was given by the solution to the Levy problem, and it was solved in 1953. Mind you, the problem was stated in around 1910, but it was solved after 25 years or something. So the problem was well stated earlier, but it took time, some around 25 years or something, to solve this problem. So it was solved by Oka, Bremerman, and Naugat. Now this is very interesting thing because now Levy problem has has still some unsolved problems of say linear problem is not a one problem. Actually, there are there are many variants of this problem, and some of the variants are still unsolved. So this is an open problem. I guess it is still an open problem in some variants of it. So the next result is the Riemann mapping theorem. So Riemann mapping theorem is a very celebrated theorem in single complex variable, and alas we can't extend it to the several complex variable. So Riemann mapping theorem states that if I have a open connected set of a proper open connected set of a complex plane, then I can biholomorphically map this set G to an open unit disk. So let me define what do you mean by biholomorphic. Biholomorphic means I have a function f which is 1 1, which is on 2, which is holomorphic, and its inverse is also holomorphic. So in single complex plane, we can characterize open set to we can actually map an open proper open connected subset of C to an open unit disk. But this startling result fails to even hold for in Cn n greater than 2. Why is that so? Because I stated before, ball and polydisk, which are very two interesting objects. So polydisk in a single variable is just a ball, but if you increase the dimension, ball and polydisk are two different things. Though they are homeomorphic topologically, but they are not biholomorphic, which means that and then how is this failing Riemann mapping theorem? So in Riemann mapping theorem, if I have a set G, I'll map it to say with F to a open unit disk, and then if I have another open set, say G tilde, I'll map this again with the function F tilde to the open unit disk, and I can have a biholomorphism between any two open connected set, proper open connected set. So G tilde will be the biholomorphism between any open connected set G and G tilde. Observe that ball and polydisk are actually open proper connected set in Cn, and they fail to be holomorphic, and thus Riemann mapping theorem fails here. So we can't use Riemann mapping theorem in higher complex plane. So that's what I have planned for this talk, and let me sum up this with a meme. So single complex variable was beautiful in its own sense, but we have extended it in a higher complex plane. It became more beautiful in the sense that it holds still the important properties of a single complex variable, and again gives us something more important, something more richer than the things we have in several complex than in the things we have in single complex variable. So that's all. These are some of the references which I have used. So the motivating article which made me do this talk was this article, What is Several Complex Variable by Stephen Kranz. And the two references which I have used is Grauert, which is a classical text in several complex variable, and R.C. Gunning and Rossi, which deals related to algebraic, which has statement related to algebraic geometry. Thank you.